All right. Well, good morning, everybody. This is Jomo Stewart and Mr. Roger Burgraff here at the Fairbanks Economic Development Corporation. It is Tuesday, February 21st, just after 8 a.m. in the morning, and we are here for this week's installment of the Energy for All Alaska Task Force. Just a word right at the top, a heads up, there will not be an energy meeting next week. My staff and I are being graced with a tour of Eielson Air Force Base, but that got scheduled for Tuesday. So no meeting next week, but we do have a very good, very interesting presentation for you today. So my guest is Ms. Robbin Garber-Slaght. She is with NREL, the National Renewable Energy Lab, there at the CCHRC, Cold Climate Housing Research Center, and here to give us an update or have a discussion relative to heat pumps. This is the latest in our installment of analyzing and assessing things that might help us relative to our air quality and the pending EPA decision relative to major portions of our PM 2.5 mitigation plan. Heat pumps, ground source and air heat pumps have come up as a possible component of a solution. And so I thought it would be good if we got some more information on them. And I had heard that NREL had been doing some work on heat pumps in our climate. So without further ado, not to steal any thunder, Ms. Garber-Slaght, thank you so much for being here, and the floor is yours.
To unmute, I still haven't figured that out. Okay, good morning. And I understand this is a discussion, not a presentation, so interrupt me as you would. And I am with NREL, with the National Renewable Energy Lab, which is based in Golden. We are currently we are still the Cold Climate Housing Research Center of NREL, although I believe our name is changing, but I do just about everything, I feel like, in housing. I've been doing a lot of research recently in the past 10 years with heat pumps in our climate. So I get the call when people want to talk about heat pumps. So let's get started. How does a heat pump work?
Right there at the beginning, before you get started in earnest, if you could just please send our apologies to the folks at NREL, just like Alaska Land, it'll always be CCHRC to us. So
I know.
Okay.
I've been there. I've been at CCHRC for almost 15 years, so it's been hard. It's a transition.
But a good one. So thank you.
Yeah. And please let me know if you can't see my slides, because I see them just fine. But and I have lots of engineers and physicists on this call, so I'll try not to mess up the how a heat pump works definition. Pretty much a heat pump, they consider it a renewable source of energy. It's heating or cooling. It can be either. And what it is, it's a system that has a heat source. The heat source can be the outside air, especially in the lower 48. The outside air works really well as a heat source. A body of water, the soil, the ground. And what that heat source does is and it's not really a heat source. We'll call it an energy source. In the rest of the world, it's probably considered a heat source. For us, let's call it an energy source. It's when you think about the air in Fairbanks in the winter, there's not much heat, but there is energy most of the time. So what happens is the energy that you extract from this energy source is used to start a refrigerant cycle. A refrigerant cycle takes that energy and it evaporates a refrigerant. That refrigerant can be pretty standard, like R134A, or it could be something more interesting like carbon dioxide or propane. CO2 heat pumps are becoming more and more common, and they actually work at much colder temperatures. So there's some interesting materials and equipment coming out that are going to work better in our climate. But the heat source, you run a fluid, or if it's air, you run air through your evaporator, which all the refrigerant is usually in one unit. And the In the case of a heat pump or a ground source heat pump, it's a box. It's a box in the corner of our little mechanical room. It's pretty small, quite frankly. An air source heat pump has 2 units. One is outside, one is inside. But what happens is that energy that's coming from your energy source evaporates a refrigerant. That refrigerant as a gas goes through a compressor. There is electricity involved in getting energy out of a heat pump. The compressor compresses the gas, steps up the temperature of the refrigerant, and then that high temperature, high pressure refrigerant goes through a condenser where it releases heat energy into the building. They can work in reverse and extract heat energy from the building and reject it to the heat source. That would be air conditioning. And there are actually quite a few heat pumps in Fairbanks that do cooling. Once you know what you're looking for, you see them everywhere. Why is that not working? There we go. There are generally 2 types of heat pumps out there: air source heat pumps and ground source heat pumps. This top photo, oh, this is a terrible photo. Didn't get very clear. This is an air source heat pump. This is actually an air source heat pump in Wrangell. This is a photo from Wrangell. The outside unit is extracting energy from the air. Wrangell's a little warmer than Fairbanks, and the inside unit just blows hot air. The inside unit has the evaporator and a fan in it. This type of air source heat pump is called a mini split or a ductless unit. And this actually has a refrigerant line that goes from the outside to the inside. These take a little, these to actually take a refrigerant technician to install. They do work at colder temperatures though. So that's the trade-off there. This head is what you get. It is pretty standard. If you're going to install one of these units, you get one of these heads in your house and it has to be installed on the wall, and that's kind of what it looks like. It's not unobtrusive, we'll just put it that way. Ground source heat pumps. This is a ground source heat pump. All the refrigerant cycle is in this box. This is the one at CCHRC. Ground source systems have an extensive heat sink that is in the ground or in a body of water. This is the install we did at CCHRC. These were 1,000 feet of slinky coil. So if you pull it out straight, it would be 1,000 feet long. In total, we had 6 trenches for this heat pump. So it was pretty extensive install. They do work at colder temperatures outside. So that's kind of the improvement in the ground source system, although they are much more expensive to install.
So actually, if you won't mind going back for just a moment.
Sure.
So as always, everybody, this is it's as much for you as for me. As Robbin mentioned, if you have any questions, if you have any comments, please do feel free to put them in the chat, throw up your hand, or simply take yourself off mute. But I'll go ahead and start the show. So on that top, the air source heat pump, is that a direct protrusion? Like, would they be inside and outside the house in a straight line?
Yes. They don't have to be in a straight line. It's piping, it's copper piping that goes between the two. But you do have to have two pipes, 2 copper pipes. I think they're like the one is a 1/4 inch and the other is a 3/4 inch. It depends on the unit, and then an electric line that goes between the two. So you have to have something through the wall. They have to be at least 10 feet apart, but they can be in not a straight line. And you can get these air source heat pumps that service multiple duct heads. So I think you can probably get up to 3 heads per outdoor unit. And
in this case, the head would be the inside the home.
Yes.
Heat or heater exchange unit. Okay.
Yeah, and it's they tout these as replacements to like your Toyo, to replace a space heating device that is usually in one room.
Okay.
Yeah.
Okay. And then regarding the bottom pictures, that doesn't look to be more than maybe 5 feet deep, 6
It is
feet.
actually 9. It is 9 feet deep.
Oh, it's 9 feet deep.
Yeah.
Okay. Okay.
And this, our location, the CCHRC building is on permafrost. So you want to get, you can actually see the line of frozen soil. This was dug in the spring because he was worried about slumping. This line is at about 4 feet. So the freezing from the top down was about 4 feet down. That's our active layer. 30 feet down, we have permafrost. Excuse me. So this is at 9 feet. It's well below the active layer, but well above the permafrost layer. This kind of install is pretty rare. We have a lot of bedrock also, so we couldn't really do wells. We also have the permafrost soil, which doesn't have great heat transfer. The way this system works, the reason the system is efficient is because what we're doing is we're freezing the soil. So what we're extracting phase change energy. And then we have enough groundwater movement that after, we freeze it all winter long, and then in the spring and summer, the groundwater moves through, the rain moves through, and it thaws it out. And that's where our energy sink is. Our energy is in phase change.
Okay.
So the permafrost is not ideal for ground source heat pumps. We'll just put it that way. It's doable. I know of at least one system that's installed directly on permafrost, but I would not recommend it.
Okay, and you certainly wouldn't want to reverse the flow so that you're pumping heat into the ground in that case.
Right.
Okay.
Yeah,
So,
and I mean, there is a house out on Constitution that has a permafrost, or has a heat pump permafrost stabilization system. So the heat pump is buried, these slinky coils are buried under the house, and it's keeping the foundation frozen. It's been running 25 years or so, keeping the foundation frozen.
Okay.
Which is maybe the most expensive way you can maintain a foundation, at least retrofit a foundation. But
yeah, and that's not uncommon in commercial applications either, to use active energy to refrigerate your soils instead of the Alaska pipeline thermosiphon kind of things.
mm-hmm. And as it gets warmer, thermosiphons are sometimes need a little help, and heat pumps are more efficient than straight up freezer units, although depending on how much energy you need to extract to maintain your foundation, they may or may not be effective.
Okay. I guess the final question, we do have one in the chat. How deep do the trenches need to be? We've talked about how deep that one is and others, but how deep?
Yeah. In general, the models that we've done say between 8 and 9 feet. That's where the trenches go. More often than not, if you're installing a ground source heat pump, you're not going to have slinky coils. You're going to have wells, which are drilled in Fairbanks. The general depth of those wells is 200 feet. If our system, which has 6,000 feet of pipe, were to be transferred and into a deep well system, we probably would have had about 3 200-foot deep wells instead.
Okay.
Is there a rough estimate of the cost of one of those wells?
One of the wells, no. I will tell you right now, there is not a single installer in Fairbanks who is doing these installs. And I get phone calls weekly who can install the system. And I just worked with the Army Corps and they ended up hiring somebody from Montana to come up and do the system. So it's not, right now, I don't know, John.
And
I
what's,
mean, when we installed our horizontal loop system in, what was it, 2012, it was $40,000. That was before the installer at the time, Alaska Geothermal, before he had a drilling rig. The price is certainly, well, the price came down before he stopped doing installs, but I don't remember what it came down to. I'm sure CCHRC.org has a paper on its website about, we looked at case studies of, I think, 9 installs. It was in 2016. There are install prices in that paper, but I don't have any off the top of my head.
Chris, I see you taking yourself or turned your video on.
I just wondered what the background was, why the installers have not been able to stick with it. If there was any, seems like there's a demand, but not there's a supply problem, or maybe it's the cost problem.
Well, I will say, I mean, when we installed this in 2012, diesel was $4 a gallon. So there was a big demand. And then fuel prices went down and there wasn't a huge demand. The kind of break-even point with our current electric price in Fairbanks, which, 25 cents a kilowatt hour. The break-even point for diesel is it's like $2.70 a gallon. If it's above $2.70 a gallon, this is cost effective. If it's below $2.70 a gallon, it's not a cost-effective solution. As fuel prices go up, I get more phone calls.
That obviously depends upon an installer. If you can't actually get it, then it's
right,
relevant.
exactly. Yeah, exactly.
And that's been a problem of having.
Yeah.
It's not something for take some specialized tools to make it cost effective.
Right. In fact, I will say the installer that we had in 2012, he probably put about 100 of these units, the ground source units, in Fairbanks. And then oil prices dropped and he didn't have any demand. So he took his equipment and now he drills wells. His equipment is up on the North Slope right now. He's drilling for the oil companies.
Actually, that was going to be my question, because we do have a lot of people who have well water as their water source, but this is a different and specialized kind of drilling.
You can drill it cheaper because it's a 4-inch diameter hole. So you can do a smaller drill, which would make it less expensive than a water well, and you don't have to case it. But water well, in fact, I think the one that NREL installed, the company they hired out of South Dakota contracted to the local water well company to drill the wells. So yeah, local companies. And yeah, there are a few, there was at least one system on Wainwright that the local water driller drilled those wells as well. Yeah, the installer had, the smaller drill rig, but his limit was 200 feet. That was as deep as he could go. But he also had directional drilling. You can install these directionally too, so you don't have to have a really deep well, and you don't have to dig a deep trench anymore.
Ms. Bergerath.
Robbin, are you familiar with what Journey Church has? Evidently, they heat their large building, the church there, with that system, and it's quite amazing, but how they're able to heat it without, I don't know whether they have a standby deal with oil, but
You know,
I think it's, yeah,
that's
you
the
probably know more about it than I do.
that's the large church over by the airport, correct?
Yeah,
Or near,
right.
yeah, oh yeah, yeah. I know it's a fairly big system. I don't know much about it beyond that. That system was installed after I did a lot of this work, so I do know it's over there. But and I don't know. It's fun to drive by buildings and say, oh, that one doesn't have a stack. I wonder how it's heated, and try to figure it out. Because if it doesn't have a stovepipe and it doesn't have an exhaust of some sort,
Yeah.
it's electrically heated somehow. It's different.
Yeah. Well, they have a fairly good sized pond, which they
Yeah.
gather the heat from. But it is quite interesting.
Yeah, and that one was a new building. It's easier to install a heat pump in a new building from the ground up than it is to go into a building and retrofit.
Uh-huh.
Yeah, for certain.
And we have had the discussion several times. I mean, the groundwater table's only 12 foot down here. It's infinitely
Yeah,
34 degrees, 12 foot down. So, but we just can't make the economics work of, certainly can't contaminate the aquifer. And, but now we have huge contaminated aquifers with PFAS, so maybe we don't care anymore.
yeah. Well, the heat pump itself, the ground source heat pumps are closed loop systems. So like our pipes run methanol. We have a water methanol mix that runs through the pipes.
They're single wall, and that
Yeah.
sometimes the regulators get a little excited about that.
Yeah, Delta has just so much groundwater. I continually try to encourage them to move in this direction, but trying to because you can do a ground source heat pump with an open loop where you just extract well water, but our well water is too cold to do that. Because what happens is the fluid comes from the ground loop into our heat pump. It comes in at about 32 degrees. It goes back out at about 30 degrees. So you can't really extract well water at 34 degrees and try to send it back into the ground at 32 degrees. It would be ice. It would freeze everything up. It would not be pretty. But like in Seward, they're using seawater, straight up seawater through their system
Mm-hmm.
as their heat sink.
I did put in the chat. I found this links on the CCHRC website relative to ground and air source heat pumps, at least a list of reports. And so I did post that in the chat box.
Oh, good. I don't seem to see the chat. I could probably figure it out.
It's okay.
So when I talk about how these are partially renewable systems, what you're doing is you're getting a lot of energy from your heat sink or your energy sink. And what the energy that you're paying for, the electricity, supplies a part of what you are delivering to the building. So like the heat pump at CCHRC, for every 1 unit of electrical energy that goes into the building, we get 3.5 units of heat energy. So 2.5 units of energy are coming from the ground, and 1 unit of energy is coming from electricity, as opposed to electric baseboard where you just get 1 unit of energy because it's all electrical. So it is efficient. It can be efficient depending on your install, especially when you start talking about air source heat pumps, because the temperature of the air outside really affects how efficient your system's going to be. But I will talk about COP a lot, so just keep that in mind. COP is the efficiency. So like a boiler is, say, 90% efficient. A really good boiler is 90% efficient. You get 90% of the energy, the diesel energy that goes into that boiler goes into the house. A heat pump is 300% efficient. That's kind of the difference. The COP of 3 is the 300% efficient unit. And it does depend on temperature. These are actually heat pump. This is a heat pump in North Pole. It's outside of HVAC Inc. in North Pole. Notice it's got a lot of snow on it. They use it in the shoulder seasons. They have these are custom fabricated hoods to try to keep the ice and the snow off of these air source heat pumps. But as it gets cold, they turn them off. The colder it gets outside, the less they run them. They have diesel backup in this building. Air source heat pumps in Fairbanks need backup, some kind of backup. They also need defrost strategy. Even though it doesn't seem very humid in Fairbanks, the heat pumps, the units outside get very cold, and they do attract moisture, and they do get frosted. I have a photo of a very frosted unit, and they are exposed to a lot of snow and inclement weather. These, I can tell, have been sitting idle by the amount of snow on top of them. They have fans that blow up and blow the snow off the top if they're running. So these, and they are not covered in ice. So these were turned off at some point and have been sitting idle most of the winter, I would say. Heat pumps, you can extract more heat from the ground than you put back. Like you can preserve the permafrost. You can certainly create permafrost. And if you are freezing the soil, you're degrading the ground, you're lowering the temperature, and you're losing efficiency in those heat pumps. And they do have high installation costs. More and more, we're getting more and more air source heat pumps in the state of Alaska, especially in Southeast. There are actually more than you'd expect to see in Fairbanks. This is a study ASEP did. Oh, sorry.
Robbin, can we go back to that last picture, please? This is Doug Isaacson. So I have two questions that I'm curious about. This looks like a very large building. So why would they install an air source if they can't run it all year round? And the second question is, what's the reason why they don't put this under a cover, a carport or something to protect it from the elements?
It could be put under a cover. It does. Most heat pumps have a fan, so they're pulling air through them, and the fan blows straight up, and that tends to keep this. If it's running all winter, keep the snow off the top. Yeah, I mean, covered space is just precious space. So if it has its own system of removing snow, maybe that's why it didn't get a cover. They installed these heat pumps to run in the shoulder seasons. So they run until the temperature hits about 0 Fahrenheit. And what they did the cost analysis and decided that running it in the shoulder seasons actually was saving them funds. Now, when this photo was taken, it was 2012 and diesel was $4 a gallon. So in 2012, it was saving them money not to run their diesel boiler in October and November and March and April.
They are a mechanical contractor, so they have some proof of concept kind of desire to make sure things work as well. But and not sell things to people that don't work very well. But a lot of these air source heat pumps especially can work both ways. They provide air conditioning in the summertime, and you switch a valve and they become heating in the wintertime. And so they very well put this unit in for air conditioning of their office, but use it for heat until it becomes inefficient, and then they got to go to oil heat or gas heat.
And I will say these are pretty efficient air conditioning units. If you drive around Fairbanks, check out dental offices. There are air source heat pumps at most dental offices in Fairbanks. They have some kind of crazy cooling load that they need, and almost every single one has an air source heat pump outside of it.
Interesting.
Yeah.
With the hospital as well?
The hospital does not have heat pumps. The hospital's a much larger load. They're dealing with the cost-effective range of these things is in the residential world. When you get to commercial size stuff, that's more direct refrigeration cycles, and there are larger units, but they just become prohibitively expensive.
Okay. And I guess that was my question relative to the picture earlier that you said was installed at CCHRC. Precisely how big a space was that intended to heat?
Well, that building is incredibly efficient. It heats a 5,000 square foot office part of the building. It's a residential size unit, though.
Actually, yeah, that's true. It is.
Yeah.
The building is incredibly
Yeah.
efficient. Yeah. Okay.
Yeah, and that is a residential unit, because Chris is right. As the units get bigger, the commercial units are pretty expensive.
How big
And
was that kind of relatively? 3 feet
That-
by 4 feet kind of thing by?
It's 3 by 3. It's a 3 by 3 foot cube.
Ah,
Yeah, it's yeah. I mean, it's in the back of that mechanical room at CCHRC. We were able to squeeze it in because it is so small.
oh.
Yeah.
Okay. Thank you. All right, do we have further? Oh, yes, please proceed.
Yeah. Was there a question? I'm sorry.
I didn't see one, no miss.
Okay. This is a study that ASAP did in 2017, and it looks at installed costs of heat pumps around the state. And there's a lot of questions about cost, so I stuck this in here. I don't know much about this. Most of these units were commercial size units, and most of them are not in the Fairbanks area. These few down here that are in the low cost for lows installed size are residential. Anything down here is certainly residential. I will say, oh, that's a very expensive, very small unit. The cost is kind of all over the place. In 2017, it was all over the place. And a lot of these are commercial. The affluent seawater ones are the Stewart Sea Life Center, it's Auk Bay in Juneau. So those are fairly large commercial systems. Some of the large air source prices have to do with the Juneau Airport. The Juneau Airport has ground source and air source heat pumps down there. So the cost per size of the unit is kind of relative, although the bigger the unit, certainly the more expensive it seems to be. And this one right here is the CCHRC heat pump. So at $43,000, it's the cheapest one on this chart. Oh, sorry, no, not that one. The horizontal, the yellow one right there, the cheapest one on the chart. And then just to give you an idea of efficiency versus temperature, this is degree Fahrenheit. And this mini split actually was in Dillingham. And it's an air source unit. Tom Marsick, it was the one in his house in Dillingham, and its efficiency is like 1.5. That's a really low efficiency for a heat pump, just in general. That one we studied in 2016, I believe, and it was certainly air source heat pumps have improved since then. So this one, actually, this Weller heat pump, mini ground source heat pump, that was actually at Weller Elementary School. It was a combined recharge system. We were using solar panels to recharge the ground in the summer. And notice the ground temperature at Weller Elementary School is really warm, 45 degrees. That's unheard of in Fairbanks. It's because we were recharging the ground. We were putting a lot of solar energy into the ground. And part of that was because it was a school, they didn't need any of that solar heat in the summertime because there's nobody in the school. Another building or a house might use that to heat hot water.
That's an interesting pairing.
What's that?
Uh, Yeah. That's interesting. And so using not the solar to power the unit itself, but actually to recharge the thermal profile of the ground. That's been a long conversation with our heat pump at CCHRC. Should we just recharge the ground? It really depends on the soil you have. Weller, it's in the hills. It doesn't have moving groundwater. It's kind of fractured schist is the soil type. So a lot of the solar energy that we put in the ground, it heated the ground, but a lot of it also migrated away. If we were to try to put that into, say, moving groundwater, it would heat the groundwater, but it might not stay on site at all. So that's I'm doing a project over on Fort Wainwright. We're looking at a new heat pump installation, and a big question that we have is we want to store waste heat. I mean, the power plant has a lot of waste heat over on Fort Wainwright. Can we take that waste heat and inject it into the ground and use it over the winter to power a heat pump, or to be at least the heat sink for a heat pump? And it's the big question is the groundwater. If the groundwater is going to take all of our heat that we're putting in the ground and pull it away. So that is actually, we're working with the state geologic survey to figure out how that groundwater is moving over there. Mr. Burgraff.
Yeah, I have a question. The heat pump is interesting and can be very useful to operate in certain areas. Now, I wonder during the summer months, when it's warmer, is there any way of capturing that warm air and putting it back into the ground, so that you'd be able to utilize that heat source during the winter months?
Is that kind of what it's doing when you're air conditioning anyway?
Yep. Yeah. So like the heat pump at the CCHRC delivers heated water to the floor. We could reverse it in the summer because we do actually have a cooling load with all those windows on that building. We could reverse it in the summer and extract heat from the floor and send it back into the ground. The problem we're going to run into is we're going to cool the floor to the dew point, and we're going to have a wet floor. If you have a unit that is air sourced, that delivers hot air or cold air, you can do that. You can cool the air in the building and return that heat into the ground.
Robbin, there was a system out in Fox where the guy installed a slinky in the ground, and then he had a little sort of a conical arrangement of pipe up above the ground that got warmed in the summertime, and then used a little solar solar electric heat pump to pump the water, to reverse the water and run the heated water that was heated by the sun back into the recharge area.
Yeah, and that's actually, that was a fairly effective system with his little, it looked like a little Christmas tree of black pipe that he just heated in the summer. Yeah, and that's, I mean, if you're concerned about losing efficiency over time with the heat pump in the ground, if you're gonna like create permafrost or something, that is certainly an option.
We do have a question from Doc Seifert. Excuse me, Weller, did the soil slowly dry out?
Weller was so dry. The soil was dry to start with. I suspect it was very dry by the end of the project. We did not keep track of the soil moisture in that project. That was a ground to air unit, so we were heating makeup air for the school with that unit. The design of the unit on the school side, so it was pulling the makeup air through a heat pump. The makeup air duct is like 7 feet wide. The heat pump duct was like 4 feet wide. It was pulling, 4 feet of air out of this giant 7-foot duct. And it was not incredibly effective at heating the air. The school district didn't run it for very long.
Thank you.
Mhm.
Okay, any further questions? Okay, we'll start to move along. And by the way, Mr. Colette, I haven't missed your question. I just figured we'd get to the money part a little later. Okay.
Oh, I found chat. I just found the chat. So this is I'm going to talk about air source heat pumps really first, and then I'll talk about ground source heat pumps. This is pretty much the fundamental problem with air source heat pumps. The colder it gets outside, the less heat the heat pump can deliver, which is counterintuitive because your boiler is always going to deliver the same amount of heat. But because it's extracting energy from the outside air, the colder it gets outside, not only the less efficient, but the less actual ability to deliver heat, the air source heat pump. So it's there's the Department of Energy is actually working on this problem, and the solution, unfortunately, is to beef up the electric resistance backup heat in these air source heat pumps. So as the colder it gets, the more straight up electric resistance heat the heat pump is delivering to the building.
And that's some of the most expensive heat we have.
Exactly. And that's kind of the real challenge with air source heat pumps. I will say they are getting better at colder temperatures. This is this study we just completed last year. We were looking at the ductless, the mini split units. We looked at them down to 13 below Fahrenheit, which is what the Department of Energy rates them to. Nobody really rates them below 13 below. We have run some below that temperature. Some of them have actual efficient function below that temperature. We're looking at a new one. Actually, it just showed up in our building. We're going to look at it. It claims to actually be efficient at 30 below Fahrenheit. We'll see how it goes. But nobody really has tested it outside of the manufacturer. But yeah, you can see the blue line is kind of the line you'd expect to see in a heat pump, because that is the line where it's running at maximum capacity. The dotted line is the maximum efficiency. These are variable speed heat pumps that we were studying. So they had 3 speeds, and we kind of forced them to run at all 3 speeds to see which was the most efficient speed. But the lower the speed, the less heat you're going to get from the unit. I think we looked at 4. We were looking at 4 of the mini split ductless units, and even at 13 below, they're averaging above a 1 a COP of 1, which would be electric heat, which is better than the study we did in Dillingham in 2016, where the heat pump actually had less efficiency. It was less efficient than electric heat because of its defrost cycle. So they're getting better. They're getting better at cold climates.
And the rub here is that, of course, for us, then you need, let's just call it a boiler.
Yes,
From
you need a backup system.
from -10 to -40, and so therefore you're paying. You've got all the infrastructure of a boiler. The heat rejection of the boiler does not go to the mini split unit, so you need the fin tube. You need all
Yep.
that capital cost of everything. So it works if you're using this as air conditioning in the summertime and you use it as heat for as long as possible, but you still gotta have the boiler for.
Yes, in
The cold
Fairbanks, you
conditions.
need a backup.
And that, Juneau, they don't need the boiler, so therefore it's a complete
Yep.
replacement system.
Yeah, I mean, it's interesting to me. Northwest Arctic Borough has been installing a bunch of these ductless systems, and they run them to about 0. At 0 degrees outside, they turn them off. But they also have been installing them with solar panels. So they kind of run only when they have the solar electric panels. Yeah.
Is that 0F or 0C?
0F. Yeah. So I touched on this already. The different kinds of ground source systems. We have all 4 of these kinds in Fairbanks. There are, I think, 4 lake loops out on Chena Pump Road in that lake. They've been out there since 2009. There are lots of slinky loops, although for the most part, there are more directional drilled systems and more vertical well systems in Fairbanks at this point. And those are cheaper to install and they take up less space.
The vertical and the directional drilled.
Yeah. Well, directional drill doesn't take up less space. It takes up less space on the surface, so it's easier to install. The vertical wells, certainly. But yeah, you can't do directional drilling into your neighbor's yard, but you don't have to dig trenches to install it. Yeah. This is the coefficient of performance, and I have more information on this system because I've been studying it since we installed it in 2012. I will admit that it is not running right now. It has not been running since November. It's the heat pump itself has failed. The compressor in our heat pump box, our 3x3 box, has failed. It was incredibly efficient, and we just need to replace the heat pump itself. The ground loop is still there. The ground loop is still functional, and we can still use it. So the big cost of our system was digging all the trenches and putting in the ground loop. That's still there. That ground loop supposedly will last for 50 years. Heat pumps themselves, they last about as long as a refrigerator. Ideally, you're going to get 15 years out of one. We got 8 years out of ours. But it ran very efficiently, except when it was broken.
Like my car? Oh,
Yeah. So that is, our average COP is about 3.5. And that is pulling 32 degree fluid out of the ground, freezing the ground all winter, and then having rain and groundwater thaw in the summer. We have not reversed the system just because of the wet floor issue. There are things we can do probably to have a little cooling. It probably take a lot more paying attention to the system to figure out. Might take a lot more controls to figure out how to avoid the dew point on the floor.
Might you install a cooling loop in the ceiling since cold falls?
We could do a radiant cooling loop in the ceiling. It's just, it's just cost of a retrofit.
Cost.
Yep. Yeah.
So regarding the mechanical failure, you say the compressor went down.
Mhm.
You say but it did run for 8 years. Do we have any?
Often.
Is there any? Do we have any theories on why the compressor failed at half-life?
We had our installer Andy likes to call our heat pump a lemon. It was the unit, the company that produced this unit was bought out, and this was the unit in like the interim between the old company and the new company, and we've replaced a lot of pieces on it, but we had our control valve failed, broke up, probably filled the compressor with gunk. We went through, we cleaned the refrigerant out of the system. We had to have a refrigerant contractor come in and clean the system, because that's one of the biggest dilemmas with these systems is they run on refrigerant. Refrigerant is highly regulated by the EPA, and you have to have a special permit to work on them. Luckily, we have a lot of freezers in town, and a lot of people who work on freezers can work on these units. They're kind of specialized, but the control or the valve failed, broke up, pieces got into the compressor, shortened the life of the compressor.
Okay.
Yeah.
Mr. Miller, you kept taking yourself off mute.
Yeah, I'm just, it's a little bit of a catch-22. We don't have as many refrigeration techs in town as we do boiler techs, and boiler tech is really straightforward. Like even Toyo tech is straightforward compared to sometimes refrigeration can be. So it's just a specialty. So it's like as we get more, we get more refrigeration techs. It'll come with time, but there's only a few refrigeration techs in town, and there are not countless people that can get a boiler running when it's 40 below.
I have heard Altrol now can maintain these.
Yeah.
So
and they're all somewhat proprietary. You got to have their parts. You got to have their things. It's not a Beckett burner that everybody's got one sitting in the garage.
Yeah, and I will say, I mean, so every empty hole in this chart is when the heat pump wasn't working.
Okay.
And it wasn't working for that length of time because we had a hard time repairing it. Although it actually froze. The heat pump failed January 2021, and it was 40 below outside, and the ground loop froze where it came into the building. The methanol mixture, it's water and methanol. Its freeze point is -5 Fahrenheit. As long as it's in the ground, it's fine. As long as it's in the building, it's fine. But that 40 below day where it was coming into the building, it froze. And that was difficult to thaw. It took quite some effort to get that thawed. We have a backup diesel boiler.
Okay. We do have a question in the chat. Would a slinky loop downstream, say from a power plant, work efficiently year round? Like say, could the Carlson Center use a heat pump to heat the facility?
I would love to see somebody extract heat out of the China.
The ANSEP crew, anything in a river is difficult.
Right.
Because the river is dynamic, and the river tears it up, and the ice tears it up. And so rivers are just difficult to utilize. Lakes work much better.
Yep. Yeah. I don't think the China is deep enough to really protect protect the slinky coils. But it is certainly, yeah, there's got to be some way to get that energy. And I don't know, I mean, yeah, the power plant is dumping heat into the river, but the power plant could dump heat into the groundwater or something else. But it could also, yeah, I mean, there's lots of uses for the waste heat off the power plant that just cost money.
Yeah, the long adage, every power plant's got the same issue. There's not a lot of great uses for 80-degree, 70-degree water. You can't heat your house with 70-degree water. You can't grow, you might be able to get it into a greenhouse or something, but that's a lot of effort, a lot
Right.
of capital to move around 70-degree water. So it's just not it's very low quality heat. Lots of it, but
Yeah. And
no.
and a heat pump can certainly use 70-degree water. It's just the cost of infrastructure to set up a heat pump and you could even run that water straight through the heat pump system because it wouldn't cool to freezing.
The hatchery was thought to be the thing that would use that 70-degree water from the power plant. And that all didn't work out because of capital.
Dr. Davies?
Yeah, we looked at a little bit a while before I left CCHRC at the possibility of adding a little bit extra heat to the, for the water in the water systems that are circulated, and then putting small heat pumps in each house so you've got say 50-degree water that's coming in. If you added a little heat to that water before you pumped it around so it's 55, then you could use some of that heat and have the water exit at 50 again. It seemed like that could work, but it required a lot more political coordination than we were able to muster at the time.
I believe Golden Heart has one of those systems installed, John. I don't know who was responsible for that. I know Andy worked on installing one, but I don't know what happened to it.
It'd be interesting to know because that distribution, that's one of the expenses of a district heat system is the distribution system. But if you're already, distributing water to people's houses, and you could just add a little heat to that water, and then enough just so you could extract it to heat the house. That might be a pretty interesting system.
Yeah, I could ask Andy who he worked with over at Golden Heart, but I don't remember who it was.
Okay. We have reached the top of the hour, but this is great conversation. So we're just know that I'm good to proceed. So if you still have time, please.
Yeah, I have a few more slides. This is kind of my big my big question when somebody calls and says, I want to install a heat pump. My question is, what kind of heat do you have in your house right now? It's pretty easy to weed out which houses are going to be able to get a retrofit heat pump versus which houses are going to have to do pretty intense HVAC retrofits. Because heat pumps deliver fairly low temperature heating fluid. Forced air, well, that's a terrible picture too. Forced air works really well with heat pumps. They do deliver colder than furnace air, but they still are able to heat houses in Fairbanks with forced air. Hydronic in-floor heat works really well because you can heat a building that has in-floor heat with fairly low temperature heat. I'm talking about 110 degrees is the max heat you can get off of a heat pump right now, although they're getting better. The higher the temperature that comes off the heat pump, the lower the efficiency. We can heat our building with our heat pump. In the shoulder season, we can heat it with 80-degree fluid. We have a system that tracks the outdoor temperature and changes the temperature that's coming off the heat pump based on the outdoor temperature. The hottest temperature we get off of our heat pump is 107 degrees Fahrenheit. But we can still heat our building, although I will say there is one office space in our building that doesn't get warm enough. And it's because the in-floor heat is not, the tubes in the floor are not close enough together for that 107 degrees. Baseboard takes about, at least 160 degree fluid. That's what your boiler can deliver. A heat pump is never going to be able to deliver 160 degree fluid. If you have baseboard, I discourage you from getting a heat pump, trying to use a heat pump with your baseboard. In fact, every heat pump failure that I've seen has had to do with baseboard. So you can have a heat pump with a backup boiler. So you take the heat pump, it heats your fluid to 107, and then your boiler boosts it up to 160. Oh, John, you have a question?
Yeah, just so I guess I'm wondering if you were going to retrofit a house that had baseboard, and you were going to keep the boiler system as your backup system. In other words, you might be doing one of these seasonal, shoulder season heating systems. Would that be a possibility where you just leave the baseboard and the oil in place and then add a mini split to heat it, in the shoulder seasons?
Mm-hmm. It's a little complicated, but it's doable. The one heat pump that was installed on permafrost had a heat pump boiler combo to heat baseboard. It was pretty complicated. He struggled a lot with the
I guess what I'm
controls.
saying is just not mixing the systems at all. Just have a completely separate,
Mhm.
and leave
Yeah.
the baseboard boiler system as installed. You've got basically a sunk cost there, and you need, for a lot of systems, you're going to need a backup system anyway. So you might as well just leave it in place and put something else in that you can use, when the temperatures are appropriate.
Mike?
Yeah, thanks, Robin. I came on a little late. Have you discussed air to water heat pumps?
No, and there aren't a lot out there, Mike, for cold climates. That is actually, there are like 2 Canadian companies that make air to water heat pumps for cold climates, cold being 13 below Fahrenheit. They still don't deliver super high temperatures. So air to water would not really work well with baseboard still. But they're out there. They're hard to get. They're hard to find.
My son will be installing one this summer as he builds his new house. And has he talked to you at all about that?
No, but I'm going to talk to him.
Okay. Also, his place of business is heated with 10 ground source wells.
Yep.
And I'm just amazed at how well that's doing. It's a huge.
Yeah, actually, I just put some sensors on that
Okay.
to
I saw them.
calculate. Yeah.
And
Yeah, we just started looking at that one because we want to look at that one to kind of inform what they could do on Fort Wainwright.
Okay. Well,
Yep.
we're eager to see how they do. Of
Yeah.
course, like the military and anyone that was born and raised here, redundancy is always a good thing.
Yeah, I'm fascinated that they don't have anything in that building, any backup system in that building.
No, they don't. And because they have the earth, that's a pretty good backup. Yeah, I've been around that system for quite a few years now, and I'm just impressed how well it's been doing. One little box about less than 3 feet by 3 feet is heating this huge shop, office, apartment, 2 offices. And it's clear they do work.
Yep.
Thank you.
Mhm.
Thanks, Robbin.
These are actually, I pulled apart a flyer that we put together at CCHRC in 2014, just to kind of give people a first cut of, if you're thinking about a heat pump, a ground source heat pump in particular, what kind of things do you want to think about? And the big one was the cost of your electricity versus the cost of fuel oil. And this was kind of a back of the envelope calculation. If your electricity times 14 is less than the cost of heating oil per gallon, then it would potentially be cost effective. Anybody who's thinking about installing a ground source heat pump, I strongly encourage you not to do it yourself. There's a fine line between what you're going to do to your soil or your ground, and if it's going to be cost effective. It really needs to be sized properly. If it's undersized, your ground loop is going to eventually degrade to the point where you're not going to get enough energy. You can oversize it. You'll get lots of energy, but you'll spend a lot of extra money oversizing it.
Mike?
Yeah, back in the mid 80s, when we were putting the Elastic Craftsman Home program together, there was a professor at the university, he might have been emeritus, I think his last name was McKay, and he recommended that to prevent permafrost from thawing, you surround your foundation with a heat pump and heat your house while you keep your foundation solid. I thought that was intriguing. I didn't know much about heat pumps at the time, but
Yeah.
And we're still learning.
Yeah, and I will say they did install one of those over on Constitution. That one's been running about 25 years. There's a fine line though. You cannot expect, unless you have some gigantic house, you cannot expect to get enough heat from your foundation to heat your house and not jack the foundation out of the ground. That's what they did at Constitution. They started jacking the house out of the ground, so they had to back off what they were doing over there.
This professor was an engineer, and I think he spent a lot of time on his slide rule working these issues out.
Yeah, Al Veazey, actually, he's an engineer. He's out in North Pole. He did a lot of work on the Constitution Roadhouse. And actually, he loves to talk about it if you have questions. Our electric are really rough. Like back of the envelope calculation is based on a 90% efficient boiler and a heat pump efficiency of 2.5. So that's it's really rough, but it gives you a kind of a baseline to start to kind of get an idea of what you can, if you can save anything with the heat pump. Let's see. Here's my photo of an air source heat pump, a frosted air source heat pump. This heat pump is sitting outside of our lab. It's a prototype from Oak Ridge National Lab. It runs all the time. I don't think it's very efficient below 10 below. It's an air-to-air system. Its defrost cycle doesn't work very well. This photo was taken in December. We did have a rather humid fall. In December, Oak Ridge is monitoring it from Tennessee. They called us and said, can you please go out and defrost that? So we had to get one of those little buddy heaters and blow heat onto the outside unit to melt the ice off of it. We've done that twice. So, but this is what an air source heat pump can do in the winter in Fairbanks if it doesn't have a decent defrost cycle. This is a prototype, so it's not guaranteed. The other thing with
I was gonna say, again, we mean, again, mechanical defrost, like you actually using electric or some other heat source to physically defrost it.
you're using the heat pump. So heat pumps can heat and cool. When they're cooling, they're heating the outside unit. So what this one does is it reverses itself, it cools the lab, and it heats up that outside unit to defrost. Cold climate heat pumps are supposed to, I mean, this is a prototype, they're supposed to have a way to prevent the house from getting cold when it defrosts. That is usually an electric resistance heater. When this one defrosts, it just blows cold air into the lab. But a commercial one, when it defrosts, it will run an electric resistance heater and blow straight up electric heat into the space, while also sending heat outside.
Okay.
Yeah.
But I'm sorry, you were moving through this slide.
Oh, I don't read slides.
Okay.
Defrost does really lower the efficiency of the heat pump. The one that Tom Marsick had in Dillingham, when it was defrosting, it was running at a COP of less than 1. So it was actually wasting energy, trying to keep the system functioning. I will say my biggest concern with all heat pumps is there are no installers in Fairbanks. There are 2 installers that I know of. One is in Willow, one is in Kenai. There's probably a lot in Southeast. I don't know much about Southeast installers. The installer in Willow will come to Fairbanks and install a heat pump. You've got to get on his list early though. And then trying to get them repaired is very difficult. Although I have yet to find out if Altrol can actually repair our ground source system, but that's the rumor I've heard.
Okay.
Yep.
We have a number of things for which we need to rebuild capacity. I've been pushing on the home energy retrofit program from AHFC, but of course we energy raters. You know, we had a dearth of energy raters when they first initiated the program. The capacity built up, but it's been many years, and so that number of actual energy raters has dwindled back down again. And you mentioned that there was robust installation of heat pump systems for a while, but the cost of energy dropped, the capacities dropped off as well.
Yep.
So, but it's good to know. We do, okay, so we have one more question in the, well, 2 questions actually, and we may want to go back to the break-even money slide.
Okay.
But first of all, regarding defrosting, just asking how often do you have to defrost, say, one of those outdoor systems in very cold temperatures? And you said you've already defrosted that unit twice, the one that's outside of CCHRC.
Right. That unit, because it's a prototype, they're trying to figure out the defrost cycle. Ideally, you don't actually have to manually go out and defrost. It's going to have its own cycle. The colder it gets outside, the more it's going to run, but it should be in the controls of the unit itself.
Oh, and that's what you mentioned, that was a prototype. Okay.
Yeah, and it really depends on the unit and the outside temperature.
And there was a question regarding, I'm looking for it now. Have you been following the DOE progress on the heat pump subsidy, which might help with the cost?
I have not.
Or were there any funds built into some of the infrastructure packages?
Yes, there are subsidies for electrification of buildings, heat pumps, both ground source and air source heat pumps in the IRA. I was supposed to look that up. I haven't looked it up yet. Somebody asked me about it yesterday too. I keep, I just haven't had time to look into that, read
That's
whatever
okay, you're quite busy,
1,000-page
obviously.
document.
So you're quite busy, obviously.
Yeah, if anybody has read it, please let me know.
But there is supposed to be some supporting funds for installation of these kinds of systems built in those packages.
Yep.
Okay.
Mhm. Yeah, the
Dr.
Department of
Davis-
Energy. Oh, go
No,
ahead, John.
please. No, please.
I was going to say the Department of Energy is really pushing electrification of buildings nationwide. And that it heavily relies on heat pumps. So, yeah.
Okay. I'm gonna go ahead and let John, I'm gonna let Elmer go first, just because he's has his hand up. Sir, you're gonna have to take yourself off mute.
You may have already discussed about researching or locating reliable and efficient, the most efficient products. But that's, I guess, my question is some insights on where to look for reviews and that would tell about the efficiency and reliability.
For heat pumps, it's for air source heat pumps, NEPA, I don't know what it stands for, NEEPA. They post online ratings of heat pumps, efficiencies of heat pumps in cold climates. The problem with that rating system is it's completely self-reported. So any manufacturer can say, oh yeah, we tested our unit and this is its efficiency, because there's not a lot of testing of heat pumps for cold climates at this point. The Department of Energy just started a program to test heat pumps for cold climates. They're actually encouraging people to develop heat pumps for cold climates. That program testing goes down to 5 below Fahrenheit. Those are air source heat pumps. Ground source heat pumps are also tested. I'm blanking. They have an ASTM test. I'm blanking on the test organization for heat pumps. It's AHRI. I don't know what that stands for. Chris, do you know what AHRI stands for?
Yeah, it's the same. It does all kinds of commercial refrigeration
Yeah.
products. It's the refrigeration standard.
Yeah.
So I did just find that site. What is it? ASHP.neep.org product list.
Yep.
But so I'm putting it in the chat, but you did say that it's self-reported, not independently verified.
Right. Yeah.
Okay.
AHRI is the independent verifier of heat pumps, but I don't know that they publish that information. Refrigerators, heat pumps should have an AHRI sticker that says they've been tested and they are this efficient. But the Department of Energy does have the what is the name of that program? Energy Star. I think air source heat pumps that can be rated in Energy Star.
I'm going to go ahead and let you go, Doc Davies, but Robin, do you mind rolling back to that break-even slide?
This one or this one?
I can't see either yet. This one,
Okay.
or the next one.
Oops.
Oh, it's okay. Thank you. John.
Sure. Well, I was just thinking, wondering out loud here, whether we're at the stage where we could do something similar to what we did with solarized Fairbanks and do jump pump Fairbanks or something like that, where we get a group of people together and work with a single installer and try to increase the efficiencies from the installer's point of view. You know, if you have to mobilize drillers or mobilize an installer from Wasilla or something like that, and also understand the federal subsidies and have a group that got together and really figured out what type of houses would make sense to do a certain type of install and group them together in that way. And it seems like we might be at the cusp of the time when that would make sense, given the federal subsidies on the horizon.
Mhm.
I was wondering if we maybe should be seeking, say, a state grant to do a test and demonstration deployment of multiples of these systems out in the worst air quality area.
Well, you can get from the borough you can get some assistance for installing heat pumps, but the trouble with that right now is that you have to eliminate, your wood stove or your oil heat system in order to put that in. And I don't think there are very many people that are interested in doing that. So we need to get a different type of, if we're going to do that grant, we need a different style of grant, I think.
Mr. Miller.
Yeah, it was just there, it's all there. This tech is all there. It works. It's been around for a while. And remember these energy efficiency rating systems that was asked about, those are always lab tests and lab things. And what CCHRC Robbin has done is some real world in our climate efficiencies. And so I think that data is more useful because the boilers are sold as 90% efficient, 94% efficient, but only when they're installed in this optimum kind of way that uses low temperature water and all this kind of stuff. And if you take that same boiler and stick it in your house to run your fin tube, it's 80% efficient, just like your Burnham boiler was. So just keep in mind to be careful of the ratings because they have nothing to do with our environment.
Good note.
Mhm.
All right, well, everybody, we have, we're well past the top of the hour, but this has been just a great conversation. A lot of good information. And yes, Mike, I was going to open it up to any final questions or comments.
Robin, do you have a heat pump at your house? And if you were going to, which one would you put in as a retrofit?
I have a waste oil veggie boiler. I burn waste vegetable oil in my boiler at my house. I do not have a heat pump. I do have in-floor heating, so I could have a heat pump. I could retrofit it into my in-floor, although I will say I don't have concrete on the second floor, so I don't think the low temp would work so well in my house. I have a air source heat pump that has been sitting in my garage for a while now. I hope to install it this summer in our in one of our outbuildings as a backup, as a system in combination with a Toyo space heater. But I also live on the hill, and it doesn't often get to 20 below up here, so it'll probably work more often than not.
Bruno has one at his place, does he not?
Yes, Bruno, actually, I believe Bruno also has the same unit I have. But he has taken his and he has converted his from an air-to-air system to an air-to-water system, which took quite a lot of effort.
Thank you.
Mm-hmm.
All right. Any further comments or questions, everybody? All right, well, seeing none. Miss Robbin, thank you so much for the presentation. Again, there've been a lot of questions relative to heat pumps. Actually, I do see Elmer, we have a last hand, please.
Yeah, just she didn't mention what brand or what size or what the COP or what kind of anything about hers or Bruno's unit.
No, I'm not supposed to mention brands.
Okay, all right.
And I don't know, actually, I don't know the COP that we're dealing with on Bruno's unit. We'd have to ask Bruno.
Okay, thank you.
All right. Well, thanks a million, everybody. And again, Robin, thank you so much for this presentation and for your work. We're gonna all be keeping our eyes on it. Yeah, something's got to give. $4 plus fuel oil. Something's got to give. And if they're going to be potentially driving up the cost with ultra low sulfur and increased hardware at the point sources, likely to drive up electric costs, we are going to have to try to find, we need to find a solution because high energy costs are part of what got us into this mess in the first place. Yeah, when wood went from being a lifestyle choice to an economic necessity. John.
Well, I was just going to say, we also need to do it because of the environmental issues. I mean, we got to stop burning stuff, you know, for pollution reasons and for, you know, we just eventually got to phase out fossil fuels.
But that's the thing, though. The irony is the most renewable, easy and renewable fuel around, we can't burn it because of our climatic and geographic conditions. It's making too much particulates in our air shed, and that's wood.
That's why if we electrify everything, we'd be better off.
Well, I mean.
Well, the electric's got to come from somewhere, buddy. Yeah.
Yeah, right now, where is our electricity coming from?
We'd still be better off.
It is more efficient.
And it would put generally less particulates in the breathable air shed.
Mhm.
Certainly, these are much more efficient than I thought. Again, I'm used to electric resistance heaters where, again, it's grossly expensive because it's grossly inefficient. You're getting half the efficiency at the electric generation site. Then you have to transfer, you know, it's getting transmitted to your home and then you're running it through this heater. It's grossly inefficient and therefore expensive. This is definitely a beneficial technology in that regard. Big time. Well, it's been great, guys. Again, I will let everybody know at this point, we are not scheduled to have a meeting next Tuesday. I get to go have a nice tour of Eielson Air Force Base. So you all have the week off. I am going to be looking for future presentations, though, and I'm always looking for recommendations. So if there's anything you'd like me to reach out on, let me know, and I'll of course make that reach out. Otherwise, again, just know that we're off next week. So everybody have a great rest of your day, great rest of this week, and a great next week also. And we'll see you soon for the next Energy for All Alaska Task Force. Thanks, everybody.
Thank you.
That is